Well, so let's get started. I'm Stephen Deppert. I'm the organic chemistry at Lawrence. I'm going to introduce Ken Grode, who's going to talk about the work he did in my lab last summer and a little bit afterwards. So Ken is a Fox Valley native from Kana, went to Kimberly High School. I work with Shannon Glenn, who is our recently named Teacher of the Year. Is that right? Did a great job. So Ken has worked really hard in chemistry and biochemistry. He is a pre-med. He's also worked with the hockey team as a manager for many years, even I think before he was a student here. So what you're going to see is Ken's synthetic work in my lab. So the way this works is that we have a challenge. We have something that we are trying to accomplish, a target to build, right? And much like hockey, the way we solve these problems is maximal shots on goal, right? So we're going to try as many different things as we can until something works. And if we run out of time and nothing works, well, at least we have a good story. But the idea is that I was really impressed with the amount of work that Ken did and the way he was able to just bring it all together and understand what he was doing. So I'll let him talk about it, and feel free to ask him any questions about biochemistry or the chemistry or the synthesis.
Thank you, Dr. Deppert, for the introduction. Like you said, I did most of my research over last summer, and some when I had the time during the school year. So like I said, my research was process towards synthesizing a target antimalarial compound. Well, before I get into the major chemistry of this, I feel it's important to first ask, what exactly is malaria? Why should we devote all this time and energy and money into fighting this disease? So first, let's start out, what is the range of malaria? Well, malaria affects primarily tropical and subtropical regions of the world. Primarily Africa and Southeast Asia being hardest hit. What's the prevalence of malaria? Well, of the world's 7.6 billion people, 3.3 billion are considered at high risk of malaria, are at risk for malaria. 1.2 billion of those are considered at high risk. Well, what's high risk? That means that malaria occurs in approximately 1 in every 20 people. And as this graph shows, both cases and deaths from malaria, you can see that we made a lot of progress over the recent years in fighting malaria. From 2012 to 2016, we saw almost a 20% cut in cases of malaria and almost cut the number of deaths in half. But as you may notice, the graph kind of ends on a flat note. We've kind of hit a plateau in fighting malaria as more and more resistances have shown up in the malarial parasite, and it makes it harder and harder to treat. So what actually is malaria, though? What do people experience when they come down with it? Well, one of the first symptoms is simply flu-like symptoms. As malaria is a disease, your body tries to fight it off. So fevers, sore throats, headaches, all things about your immune system working. Also, anemia can occur. Malaria targets red blood cells, and when you have reduced numbers of red blood cells in the body, oxygen doesn't circulate as well. So organs and other parts of your body suffer without oxygen. Also, enlarged spleen can occur. The spleen is the main part of your body that filters the blood. So if a disease is attacking the blood, the spleen is being overworked and it becomes inflamed and enlarges. This causes abdominal pain, but it also reduces the function of the spleen. Similarly, the liver can become enlarged. Not only does the liver work to detoxify the body, but it also is a target of malaria. So when the disease is present, the liver has to work extra hard just to do its job while it's being targeted. And finally, jaundice can occur, as both red blood cells and the liver can give off the pigment bilirubin when they die, which turns the skin and the eyes a slight color of yellow. But what exactly is it that's causing this? I mean, yeah, it's malaria, but what's the root of malaria? Well, that's this right here, a Plasmodium parasite seen in the saliva of a mosquito. In this form, it's called a sporocyte. It's infectious form. So how does this infect someone? Well, as I said, it's in the saliva of a mosquito. So when a mosquito goes to take a blood meal, the parasite gets ejected into the blood of the person. While in the blood, it searches to find a cell to fuse with. This can be either a liver cell or a red blood cell. Once it finds the cell, it releases biomolecules to enter. So this is lipids and proteins that allow it to penetrate the membrane and enter inside the cell. Once inside the cell, it begins to feed on host hemoglobin. Now this is the molecule that carries oxygen, but the parasite uses it to get both amino acids, proteins, and other lipids for which to build. Well, it's in feeding on the hemoglobin, it matures, and once it's mature enough, it reproduces. Now it reproduces both asexually and sexually. Its asexual offspring are called merocytes. They are what's considered the infectious offspring, while their sexual offspring are called oocytes and are either male or female. But they can infect other cells inside the body. So once it has reproduced enough, it actually lyses the cell or breaks it open because there's so many parasites inside. The baby parasites then get released into the blood and then continue the cycle of infecting other cells. But like I said, that's the merocytes. The oocytes just kind of float around and wait for another mosquito to come and take another blood meal. Now, when the mosquito takes another blood meal, it can take up both oocytes and merocytes. But merocytes will simply die as mosquitoes' stomachs aren't super friendly. However, the oocytes can pass through the salivary glands and they'll actually fuse inside the mosquito and mature into a sporocyte, which then allows the cycle to repeat into different people when the mosquito goes to take a different blood meal. So now, how do we treat this though? Well, there's two approaches. One of which is we can try and target the mosquito. But we're all from Wisconsin, or in Wisconsin right now, and as you know, it's kind of getting warm out. You may have seen a few more mosquitoes. Now, imagine living in a country that is warm and wet all year as opposed to a month. It becomes a lot harder to try and fight off mosquitoes. So instead, we have to focus on treating the parasite while in the body. So one of the first ways that we do this is with chloroquine. It's a drug discovered in 1934 by Hans Andersen. It works by interfering with parasite digestion. Normally when the parasite feeds on hemoglobin, it can convert the heme group in it to a safe pigment in its body. However, in that process, there is an intermediate that can be toxic to the parasite. The chloroquine here interferes with the digestion and stops it at the toxic intermediate that builds up in the parasite until the parasite dies. But it's at such a low concentration to us that we don't feel the effect. But unfortunately, early on in the 20th century, resistance began to spread to chloroquine. As it's a parasite, it can adapt to such things. So resistance spread out of Southeast Asia, through Africa, and through South America, meaning that chloroquine can't be used as a frontline drug for treating malaria. So since chloroquine, a lot of other drugs have come through, and a lot of them have gone because of resistance. More recently, artemisinin has been our main drug of choice. Discovered in the late 20th century by Chinese scientist Yu Tu, who only won the Nobel Prize in 2015 for her work here. It is a great drug, it's very quick acting. But the mechanism for which is still heavily debated. There's both three prevailing theories, the leading which says that this epoxide bridge reacts with the heme group to form free radicals, which then cause a bunch of unwanted reactions inside the parasite body until the parasite dies. Unfortunately, as of March of last year, 5 countries have already confirmed resistance to chloroquine, to artemisinin. So we need more drugs to fight it. But the problem with malaria is it's not a very profitable disease. It affects a lot of poor countries where pharmaceutical companies can't necessarily make a profit when they go to sell the drug. So what do we do about that? Well, we make some cool logos. These are different projects that Dr. Dever's made. Ninja Flamingo, Ninja Piranha, Zolo, Sky Moose, Aqua Snake. But what does this have to do with fighting malaria? Well, all these projects are projects that Dr. Dever undertook with his Organic 2 class with work for the Open Source Malaria Project. Open Source Malaria Project is a worldwide collaboration of labs from all varying sizes, from small ones like Dr. Dever's up to very large-scale campuses. Everything's open source and shared freely, with the goal being to produce these drugs without having to have a pharmaceutical company provide the overhead. So the idea is we've got to produce new targets for antimalarials. And once we have all these new targets, we want to flood the pipeline with drugs for testing and treatment. But what does flood the pipeline mean? Well, it's kind of an industry term to address the pipeline that takes molecules from a lab to the public. Because when a molecule is first made, it doesn't immediately go and shipped out as a drug the next day. So the idea is, with the Open Source Malaria Project, is to produce a ton of compounds that then enter this pipeline. And now some are going to hit roadblocks that are going to slow down their stream to the public, while others are going to shoot out. So by having a bunch of them, there's a constant stream flowing out. And this helps fight resistance because even if malaria comes resistance to one, there's soon other ones flowing out to help fight malaria. Which brings me to our target molecule. This beauty right here. At the start of summer, Dr. Dever showed me this, and this is what I had to make. So I need to look at this retrosynthetically and basically say, how am I going to stitch this together? So when I looked at this, I saw 4 different pieces. A methylpyridine, a sulfur, a trifluoromethyl group, and this big complex here called 1,2,4-triazole 4,3,8-pyrazine 5-chloro-3,4-difluoromethoxyphenol. I'm going to call it triazole complex because it takes a little while to spit out and I don't always remember it exactly. So you may wonder, why did I break this down so much, but leave this as a big chunk? Well, that's thanks to the worst of SMszKGAEdEo. That was the project the year that I took organic to, which was last year with Dr. Debbert, and the whole goal of the project was to make that triazole complex, which I got to use over the summer. So what exactly was involved in SMszKGAEdEo though? Well, we started with the dichloropyrazine and added hydrazine to get a hydrazone. We then took the hydrazone and reacted it with this aldehyde to get this more complex hydrazone. Once we had that, we needed to close the ring here. Now to do it, it's not quite as trivial as the other two reactions. We need to use a molecule called phenoliodine diacetate, or PETA, this cool phage looking thing here. So that closes this bridge and it makes this double ring complex. And it's a very good reaction. It gives us about 51.3% yield, which for a molecule that complex is great. But how do we know that we have that and not something else? Well, we used, for a lot of my research, a method called GCMS, or gas chromatography mass spectrometry. But what is that? Well, this is the exact machine we have in our lab, right down to the model number you can check. And how does this work? So you inject your sample into a port where it passes through some special tubing in the oven. Now, more polar substances take longer to pass through, while less polar substances quickly go through the tubing. Once it exits the tubing, it hits an ionizer where an electron beam hits your particles. Now, what it does is it breaks down molecules into chunks and turns them into ions that have a charge. These then pass through a field that accelerates them to the same kinetic energy. Then they get hit through a deflector by going through a magnetic field that deflects them depending on their charge and mass, with more charged and smaller mass being deflected more, which is then picked up and identified by a mass detector. So about half an hour after injecting your sample, in my case, you can set it for different heats and different times, but half an hour, you get something that looks a little bit like this. Now, in this case, we're going to use examples of benzene and a phenol. So each of these peaks represents a different molecule. Now, benzene, being a lighter, less polar molecule, would have a lesser retention time than the phenol, which is going to be a little bit more downstream. But as you can see here, there's a larger amount of phenol than benzene. So this is how we worked up a lot of our reactions when we didn't want to clean them up completely. So checking at the beginning of the summer, we had this, but we already had half my molecule. I just needed to assemble 3 other parts. Well, our first idea was, can we stick sulfur onto our triazole complex? So looking in the literature, we found a reaction that used thiourea that seemed to work very well with nitrogen heterocycles, or rings that contain nitrogen that also had a halogen on them, which would be chlorine. So the idea was the thiourea compound would replace the sulfur with the chlorine with the sulfur, giving you this. But unfortunately, this didn't work for us. So we returned to the literature and we found a different sulfur-containing compound, sodium hydrosulfide. But again, this reaction didn't work for us. So we thought about this, and there's a lot of complexity in this molecule. There is the possibility that the heat would break open this bond, things would fall off, things would interfere with the way we wanted it to bond. So we decided to take a back step to the first hydrazone that we had and try and get the sulfur on there, because we could always just build up the rest of the molecule. So again, we tried our thiourea reaction, and again, it didn't work. So again, we turned to our Nash reaction, and again, it didn't work. So now we take it back one step, might as well take it back all the way to the dichloropyrazine. Now the benefit of doing this is there's twice the number of chlorines, which means there's twice the number of possible sites that we can replace with sulfur. So if we can at least get one sulfur to be replaced, then we can build up the rest from there. Well, before we tried our thiourea prep, which hadn't been working well for us, we wanted to try something a little bit more experimental, I guess. We took thiourea and our dichloropyrazine and used a mortar and pestle to mash it together, hoping that aligning it in just the right way with just enough friction would make the two go together, and we'd end up with our sulfidated compound. And despite it changing colors from yellow to nice bright white and there being heat, GCMS said we had nothing. So we like this idea though. Maybe without solvent was the way to go. Maybe that's what was interfering with everything. So we found a different prep that also used thiourea without solvent, or neat, and except this time we heated up till both were in a liquid phase and stirred it for a while. And this didn't work for us. So we went back and tried our thiourea prep, but it still didn't want to work for us. So we gave our Nash prep another go, and it still didn't go. So we tried multiple ways now to get the sulfur onto the triazole complex, and it wasn't working for us. So we thought, well, maybe we can just buy a sulfidated pyrazine and then build from there. The problem is that molecule right there costs $250 a gram. Now, to put that in perspective, gold costs $40 a gram. So for the same amount, for 1 gram of this, you'd get 6¼ grams of gold. And considering this is a starting material, it's not very economical. Because if you remember back a few slides, the triazole complex only has about a 50% yield, which means by the time we get to that, we would have lost half of our starting material. And that's not even counting any times that we try to go this route. So this just wasn't feasible, so we had to find a different way. Our idea was to add the sulfur onto the methyl purity. Now to do this, we found a patent reaction that used potassium thioacetate, this molecule here, to replace the chlorine with the thioacetate compound. And this worked for us, and very well. At 60% yield, it was a very good option, and I've made a lot of good sense. So we now successfully added the sulfur onto the purity. Now all we need to do was add the trifluoromethyl group. So we turned to the research of SMszKGAEdEo, Professor Devert's student from the previous summer, who had spent her summer looking for a reaction to do this. And she settled on a radical reaction from Barron Labs. This is a really amazing reaction that deserves a lot more time to speak about and talk about, that I won't be giving it, but Samantha already did, and it was a wonderful talk. But in this reaction, you first have to make your zinc salt. So using zinc and trifluoromethane sulfonyl chloride, this here, in some water, you put them together, stir it, and you get your salt at a 99% conversion, which is really high, it's great. You then take the salt with what you want trifluoromethylated, in our case this, and you introduce an initiator to it, an activator to it. In our case it was tert-butyl hydroperoxide. And this causes a radical reaction here that, without getting into chemistry, lets the trifluoromethyl group attach here. And it worked. Very selective, very good, 60% yield of what we wanted. So we have now taken all 3 parts and made this, and we had our triazole complex, we had both halves of the molecule. All we needed to do then was stick them together. Now the modern way to do this is using palladium. It's great, it's a nice metal that likes to wiggle into halogen bonds, but can still bond to another molecule, say sulfur, and then leave with the halogen, leaving your 2 things fused together. But in our reaction, we used palladium called tris-dibenzylene acetone dipalladium. This kind of cool looking complex here. With these that kind of sandwich around it to keep it inactivated. You then have to add an activator, in our case XPhos, which lets the palladium do its job. So in our reaction, this is what we tried, but it didn't work for us. And that's not to say this is a bad reaction. Palladium is super sensitive to oxygen, which is in the water and in air. And at the time, we didn't have a great way of keeping stuff oxygen free. The lab now has a glove box, and I'd love to go back and try this reaction. But at the time, we couldn't do any better, so we kind of had to toss it to the side. So making this bond with palladium wasn't the way to go. But after thinking about it a while, we now had a reaction that added sulfur to an aryl ring. Granted, it was one removed, but it was along the right lines. So we decided to go and try our original route, this time with a reaction that we knew worked. So using chloropyrazine to represent our triazole complex, because it's a lot simpler and a lot easier to get your hands on than the full form of the complex, we used the thioacetate, same reaction, trying to get that. It didn't work. But unlike a lot of our other failures, we got something kind of neat this time. We ended up with a pyrazine dimer linked by sulfur. Now, why is this interesting? Like I said, pyridine is a ring. Pyrazine is a ring. If it could make a dimer out of the pyrazines, it might be able to connect a pyridine to a pyrazine if you introduce pyridine to the system. So this guy's thinking about multi-component reactions. But what is a multi-component reaction? Well, in a standard reaction, you have your synthetic target, in this case, say made up of 4 different pieces. So you take your first 2, throw them in a reaction, get a product. You then have to take that product, clean it up, make it usable, add in your next reagent, react that, get your next product. Then clean that up, make it usable, add in your next reagent, react it before getting your final product. Multi-component reaction, the idea is you have that same synthetic target, but you can throw everything into one pot at once and get what you want out of it. It saves a lot of time and a lot less cleaning up of your product to be usable. A good example of this is the Grode reaction. It's a reaction used to make synthetic proteins for pharmaceutical libraries, and it has a great variety of applications besides that. In this reaction, you use a ketone, an amine, carboxylic acid, and isocyanide, with all different R groups, and R groups for the non-chemistry inclined are just carbon-containing compounds or side chains like proteins have. So you're able to take all this, throw it in a flask with some water, and about 15 minutes later your reaction's complete, and you've got a pretty complex molecule. Looking at it a bit closer though, you first start out with your ketone and amine interacting reversibly to make an amide. But once you introduce the carboxylic acid and isocyanide to the system, it reacts irreversibly to give you this intermediate. The intermediate then reacts irreversibly with itself to give you your final product. So it's a really cool reaction that saves a lot of the cleaning up of product steps. So we wanted to apply this idea to our system. We knew that, at least in a model system, the triazole complex would make some sort of dimer. By introducing pyridine into it, we hope that instead of giving a dimer, it'd give us our final product. But because, like I said, this takes a lot of time to make and this takes a lot of time to make, we wanted to model it before we started wasting our precious starting materials. So we chose a model system that was a bit simpler, a bit cheaper to work with. Using our starting material, chloromethylpyridine, and again the chloropyrazine to represent the triazole complex, we hope to get this. So in our reaction, we started out by adding the chloropyrazine and the thioacetate and refluxed it in DMF for 2 hours. This should give us something like this. Then, in some time, the acetate actually breaks off, leaving a charged sulfur atom. Hopefully, by then adding pyridine after this, we get our starting product, our final product. And this appeared to work. Our GCMS data showed that we had a very large peak of what we wanted. We also had a very large peak of our dimer. So we wanted to improve on this. We wanted to be able to make a lot more of this with a lot less of this. Well, when we first ran our reaction, we ran it in a 1-to-1 ratio with excess thioacetate and DMF. So this gave us some things to play around with. We could play around with the ratio of the pyridine, pyrazine, or the solvent. So like I said, this was 1-to-1. We could increase our pyridine ratio to 3-to-1 or 5-to-1. Alternatively, we could go 1-to-3 and 1-to-5. Now, DMF is a small molecule. It's pretty polar. We could use another small molecule that's pretty polar, like DMSO. And again, play with 1-to-1, 3-to-1, 5-to-1, or 1-to-3, or 1-to-5. But like I said, both of these are small molecules. Maybe a larger molecule like diglime would be a good option. Diglime has these nice arms here that can wrap around and stabilize an intermediate. So we wanted to try that with the 3-to-1, 5-to-1, and 1-to-3, 1-to-5. So after running all 15 of these reactions, we couldn't beat our original. Now, it's important to note that we ran this very small concentration. And when we worked it up on GCMS, we saw a lot of side products that we'd never seen. So, but being at such a small concentration, we aren't able to isolate it. So the next step in improving this reaction would be to scale it up so we can isolate what is on the sides and steer the reaction away from those intermediates. So for future work, we still need to make this bond. But we have a very promising reaction that just needs to be refined. Once we can make that, the open source malaria project is interested in an oxidized version of it, where a sulfone links rather than just a sulfur. I'd like to extend thanks to the Lawrence University Excellence Science Fund for funding my research, Dr. Gubbert, my research and academic advisor. Thanks for taking a chance on me last year when I think I approached you like a month or 2 after the research deadline. And then thanks for giving me a heads up that I was hired like 2 weeks before school was out. It worked out. Dr. Sazma for being there over the summer for consultations and for helping me with this PowerPoint during this term. DMARC, who doesn't get enough recognition. He really doesn't. He always made sure we had everything. And he also let me hang out down there when it was not a good day for reactions and I wanted to be nowhere near my hood. Dr. Dave for helping me with this, and all seniors with our capstone presentations this year. And the research students in Stites 227. You guys were there for emotional and scientific support and really made research fun. And thanks everyone for coming. Any questions?
So when you tried your palladium catalyzed cross-coupling, sometimes aryl chloride bonds are less reactive than other halogens. Do you know if it'd be possible to make something like the bromide or the iodide or that pairing ring?
I don't. I assume that would be possible. I know that pyrazines can be kind of hard to make, so I assume though there'd be some reaction using a similar halogen, but I couldn't say without looking up in more detail.
What scales do you work with for the, where do you change out the ratios?
5 1,000 some more. 0.005.
It's like milligrams, how many milligrams?
Milligrams, I want to say like 7 mgs.
Yeah.
Yeah.
So you did a crap ton of synthesis reactions. This is impressive. About how long does each one of these take? So you went down so many different avenues to try and get to your final.
Yeah, it really ranges. Like I said, when we used the mortar and pestle, that was all 5 minutes. The plating one was left overnight to I think 5 days at one point because that's what the literature said. So it really depends on the reaction. When I did those 15 at the end there, those were about 4 hours apiece.
To give some perspective of like how much, like, you went down so many different paths. Was there any reaction in particular that you were really like thinking like, okay, yeah, it's totally gonna work, and then just all of a sudden you're like, this is just getting ridiculous.
That would definitely be the palladium reaction. I had a lot of faith in it, but the first time we ran it, the solvent somehow boiled out. So we went back in again, wrapped it up some more, and the solvent boiled out. Went back to the literature, found out they'd used a microwave tube that at the time I didn't realize what that was. It sealed glass, so it's kind of disappointing, and we just didn't have any way to do it at the time. But I thought it was going to be a great reaction. But yeah.
Such as research.
Do you have any future plans to try and better your ratio of product to the timer?
Again, it involves scaling everything up so that we could actually look at what we're getting as side products, because then that'll tell us, well, if it's the solvent that's altering it, since we have basically every variant there, if it's a solvent, we can try and choose a solvent that is more likely to give us the product, or if it's a ratio, we can always fix a ratio. But without scaling it up, it's hard to say what exactly we're getting, so I can't really direct anyways without that.
Would you still use palladium if you scaled it up?
Palladium was used in a different reaction, and this we were just refluxing it actually. So it was just our 2 molecules in with the salt and 2 hours of reflux.
For that same reaction, did you consider the order of addition? Because you refluxed just the 2 pieces, the salt and the 1 piece together, and then you added the 2nd piece? What if you just mixed all 3 and refluxed it all at once?
I did consider it, but it's something without running it I couldn't tell you.
Yeah.
Like some 15 reactions. I mean, I'd love to
No.
basically every possible
accusing you of
combo. I'm a big
nothing.
fan of that, but given the time period in which I was doing this, it was not quite feasible to do every reaction.
Yeah.
Okay, so more questions? Let's thank Andy.